I'll say that again. Torque is the application of a force to try and twist or turn an object. Obviously, there's something mathematical about it. But what it is the application of a force to try and twist or turn an object. It should not be confused with torque. Although there may be some twisting or turning when we deal with torque, they are different words spelled differently. This is how you spell torque. Torque, different, okay? So twerking was more popular years ago, and so everybody thought I was saying torque the whole time. I was not. I was saying torque. But I want to be clear with all of you. Torque is different than twerk. I mean, you don't have to twerk when you talk about torque, but you probably have to torque when you twerk, right? That would probably be true. Fair statement? What did you guys learn? So we use a lowercase tau as a symbol for torque, and it's obviously another Greek letter in a long line of Greek letters we've been using for this. It's lowercase, but the lowercase tau isn't actually like halfway. It's a little bit somewhere in the middle. So if you want to get an idea for the size of what the tau should look like, a T should be, of course, all the way up there, and tau is just a little guy. But he's got some flair to him, right? So he's got the little cool hat and a little bell-bottom jeans there going on. So he's fine. He's good. We like tau. Tau is a vector. It has to do with direction. If I want to open my door, what is the direction for my opening door? We talked about it. Do you remember the right-hand rule? I take my thumb, align it with the axis, and then my fingers curl in the direction. So if I wanted to describe the direction of opening my door, I know the axis is where the hinge is, and I want the door to open outwards, so I take my right hand, put my thumb downwards, and my fingers curl in the direction that the door is opening. So I would say that the door opens with a direction of spin downward through the hinge. Do you remember that conversation? Good. We're going to need that because torque is how the door opens. So we're probably going to have to come up with some way of describing the direction of torque. I want to draw the door for just a minute, and I'm looking at the door from a certain vantage point. So the hinge is over here. I put a small triangle where the axis of rotation is. This is to indicate where the pivot point is, also called the fulcrum. Okay. They can say fulcrum, they can say pivot, they can say any number of things, but be prepared for fulcrum because that's a vocabulary word. But pivot point is just as good. And again, this is the door, so imagine that we have a door handle over here, a door handle over here. I am envisioning that we are top down looking at the door. Does that make sense? We're above it, looking down upon it. I'm saying it this way because there's important details here that I think we need to flesh out. If I wish to open the door, we've indicated that the best way to do so is to apply a force to the door. And I will have less success if I apply that force over here. I will have more success as I get that force over here. You've also indicated that I will have less success should that force be directed this way. So if I have a force like that, that will be a less successful way to open the door, but that I will have more success as I approach 90 degrees. All that makes sense? All right. So I'm going to leave it somewhere in the middle. And we've indicated, too, then, that there must be something about this distance that matters, the distance away from the pivot point. Now, I'm looking top down on the door on purpose. Some of you are more altitude challenged. The ground is closer to you than other people. Does that make sense? I'm not saying anybody in particular. Some of you have lots of altitude and the ground is far away for you. When you go to the door, you probably apply your force at a different location on the door due to your diminutive or tall-like stature. Would you agree? Now, I would say that all peoples, because we want everybody to be successful, can successfully exit the room, short or tall. So all people can push at a point along A, correct? Whether they are down low or up high? Do you think it matters whether they push here for A or here for A? If the axis is over there, we still are the same distance away from the axis of rotation. So when it comes to the height of the door, I don't have to draw that here because I don't think that's going to make any difference. Now, there could be some time where that would make a difference, but not under these circumstances. Our problems are largely going to be two-dimensional in this nature. So, torque must have something to do with this distance. We call this distance the torque arm. I will use a lowercase r for it. And of course, we'll use a capital F for force. And it is traditional to use phi as the angle. And we generally measure the angle on the outside of the force, but we don't have to. Because the force can be directed in any way relative to the door, whether we measure the angle on this side or measure the angle on this side actually won't matter. And I'll explain why. First, we probably can put together that R increases the torque. If R is bigger, the amount of torque we're applying is also bigger. That makes sense? And F probably also should be up on top, meaning that if F gets bigger, then the torque gets bigger. Agreed? So together, they determine how much torque there is. But these are both vector quantities. So when you go to multiply them together, their vectorness gets in the way. This is a special kind of product called a vector product or a cross product. We've had multiplication of vectors before. We had the scalar product or dot product earlier in the year. That was the product of two vectors that resulted in a scalar. The cross product is the product of two vectors that results in a vector. So we use slightly different symbology for that, but we use like the old school times symbol, because you guys probably don't use that much anymore, but for vector products we do. Now, just a brief aside, it was work that used a similar vector product, but it was the dot product. We just had to make the dot nice and big. You remember that from first semester? When it came to work, forces in the direction of motion were more effective at doing work. So when we multiplied them out, we wanted to know how much of the force was in the direction of motion. We used cosine, because the more aligned the two forces were, the more that force was doing work. In fact, we had maximum work done by a force when the force was directly in the direction of motion, which gave us a cosine of 0. But for torque, our force is more effective when the angle gets closer to 90 degrees. So which function would we use there? Sine, right? Sine is maximum at 90 degrees, and that means more effective. So we would have R times F times the sine of our angle. Yeah, that's how we calculate torque. Now, these represent the magnitudes, but not the direction. Now, work had no direction, but torque has direction. We're going to have to handle that. Before I get too much into that, let's just talk about units for a minute. For work, it was newtons times meters, which we called a joule. Now, I know this is going to seem a little weird, but for torque, it's meters times Newton. And in every other portion of our discussion, we would have not cared about the order. For torque, we care. writing meter Newton is a specific way of communicating that you're talking about the unit of torque. It's purposeful. It doesn't have another unit. We leave it meter Newtons to signify that you are talking about the value of torque. A similar unit is the foot-pound. These are both units of how hard you're twisting or turning something. If you've ever bought and I don't know if anybody has one, I have one, a torque wrench. A torque wrench is a wrench, or even some of them you can buy are like screwdrivers, that tell you how much torque you're applying while you're applying that torque. If you've ever worked on cars before, if you over torque a bolt, you could break it. So a lot of times you're given specifics on how tight you're supposed to torque down bolts on a car so that you don't overdo it. Most of your cars have, if they're not electric, have an oil pan at the bottom of it. The oil pan is held by a bunch of screws and bolts. There's a gasket in there. If you tighten it down too much, you'll puncture the gasket and oil will leak out. Or you'll crush the gasket and oil will leak out. So they have specifics on how tight should you twist something without twisting too hard. Now we've covered that stuff, let's talk about direction. Because there has to be a way for us to figure out the direction of torque. Yes, we could probably talk about direction in one like this by talking about clockwise or counterclockwise. I mean, I think you could all probably agree the door's going to go this way, clockwise. But we have a symbology that we use here, and I want to use it. First, the direction of the torque is into the board. There's got to be a way to communicate that, and there is. To indicate a vector is into the board or out of the board, we use either a circle with a dot or a circle with an X. A circle with an X is into the board, and a circle with a dot is out of the board. I want you to imagine it's like an arrow. If the arrow is coming at you, you would see the point of the arrow. If the arrow is pointed away from you, you would see the fletching of the arrow. Does that make sense? That's kind of where it comes from. So if I wanted to describe the direction of the torque, I would say the torque is in that direction. I could say into the board is positive or into the board is negative. In fact, it will not be uncommon for you to have a picture presented on your exam and something like this off in the corner telling you the positive directions that will be used in the problem. This is telling you to the right is positive, up is positive, and out of the page is positive. Everybody understand? It's a way of drawing three-dimensional things on a two-dimensional plane. Right. So we have the basis of torque. Good to go? Obviously, torque being the way it is, there's going to be a little more complicated to deal with. But understand now that just because it's more complicated doesn't mean it's not something we can't handle. We've done static problems before, so we're going to talk about torque from a static standpoint for a little bit and deal with static problems. And this opens up an entire group of questions that we couldn't talk about before. The first example I'm going to do is a bridge question. But a static problem is one in which the object in question is experiencing a net force of 0 and a net torque of 0. For most statics problems, we're dealing with problems that do not move or objects that do not move. If you want to design a building, that's a statics problem. Or the configuration of poles and cables that hold streetlights, that's a statics problem. You do that to figure out the forces and therefore the types of materials you might have to use in order to withstand those forces. But we've been doing statics problems just as net force problems. But now we have enough information where we can bring in more information, more things to bear. So a statics problem, we state that the net force and net torque are equal to 0. Consider a bridge. Imagine I have a bridge that spans a canyon. So I have like canyon walls coming up here. giving way to the roadway. Not a whole lot of canyons in Florida, but we have lots of bridges, so it's okay. And so cars, as they travel, will travel and approach the bridge and eventually navigate the bridge. Or elephants, apparently. So the bridge is suspended, or is in place, due to two pylons. And I'm purposely making the pylons asymmetrical. Maybe that's just where they could place them. All right. Let's say the bridge is 300 meters across, and we'll say that this is 60 meters from one edge and this is 40 meters from the other. That okay? Just give them some basic ideas here, some basic stuff. And let's assume the bridge itself is of uniform mass. That would mean that its center of mass is in the middle. All right, you guys all got that now? Right now, it's easy to draw out the net force problem. We know that there's probably three forces acting in this system. There's the weight of the bridge. There's the left normal force and the right normal force. Even now, I couldn't tell you what the two normal forces are. If you think about it, we're going to add up the right normal force plus the left normal force, subtract the weight of the bridge, and set that equal to 0. But if it's not symmetrical, do you think the two pylons are holding the same amount of weight of the bridge? And what happens when this car is on the bridge? Or this elephant? Which one do you think is holding more of the weight of the bridge? The left pylon or the right pylon? Probably the left, because the car is closer to it, but it's not a static or symmetric situation. Now, we could go ahead and add the car in here. Say mass of the car times G. So I'd have to subtract because it's downwards. Equals 0. But we would not be able to find the two normal forces, right? We have two unknowns. Even if I give you the weight of the car and the weight of the bridge, with the two unknowns, we can't figure out how much the pylons are pressing upwards on the bridge. That's where torque comes in. Torque can figure that portion out. To do this problem, we've done the net force problem now. This is the net force problem. Now we're going to do the net torque problem. The net torque problem isn't much more difficult, but there are other things that you will have to do. And I want to talk to you about some of the other things you will have to do. First, you'll notice in this problem, we don't have a pivot point given to us. Like, they don't specify that the bridge pivots about some point. If you're given a pivot point, you may have to use it. However, and this is what you write down, in a statics question, you can choose any pivot point you want because it's not rotating. It's in place. So, I'll say it again. The first thing you do in a net torque problem is identify the pivot point. That's the first thing you do in a net torque problem. That is different than a force problem. You didn't have to do it before. You identify the pivot point. If it's a statics problem, you can choose any pivot point you want. Hint, if you want to make your problem easier, place your pivot point at the location of one of your unknown forces. Hint, if you want to make your problem easier, place your pivot point at the location of one of your unknown forces. If you do that, what is the distance from the pivot point to that force? What's the torque arm for that torque? That means that torque is now 0. Now, your next job is to identify all of the torques acting on the bridge. So, for example, there's the torque from the left pylon. We know that's going to be 0, but I'm going to write it in here anyways. All right, this one's going to be 0. Then there's the torque from the right pylon. Then there'll be the torque from the bridge, and then there'll be the torque from the car. We have to go object by object now and identify the value of each torque. Let's make the car 2,000 kilograms and the bridge 10,000 kilograms, just to have some numbers with which to work. And let's say that the car is 20 meters from the pivot point. All good? So we've identified all the torques. Now we have to calculate the torques. You notice how I list them like this? You know at the end what I'm going to do is to say we have to add them all up and set them equal to 0. That's what I'm going to do at the end. But now we can go object by object and evaluate the torque. For example, let's handle the car. The car is located 20 meters away from the pivot point. So for the car, 20 meters. That's the length of the torque arm. The size of the force, 20,000 newtons. All right, mg, 2,000 times 10. Now, the sine of the angle. Can we agree that it's 90 degrees, so the sine is 1? Let's go to the bridge. If we assume the weight of the bridge is in the middle, then how far is the weight of the bridge from our pivot point? 90 meters. That's going to be 100,000 newtons. And I'm just going to do the last one while I have you here. How far away is the right pylon from the left pylon? 200 meters. We don't know the size of that force, but I think we can assume it acts upwards. Good so far? Now, I wanted to get this far so I could say this. Next, you need to go through each torque and determine whether it's positive or negative. You can pick. I'm going to say out of the board is positive. I'm going to say out of the board is positive. But each one of these now needs to be evaluated for being positive or negative. All right.